Hello, hello. So we are back here again. Let's do some more calculation on the pH of a weak acid. So the question is calculate the expected pH of 2 molar concentration of chloroacetic acid solution. You're given the Ka value. I hope you know that Ka means ionization constant. Now, I want you to look at that number. It's very small. This is equivalent to 0.0, I think 2014. It's small, which means this acid does not ionize easily compared to HCl. So you cannot determine the pH as asked in the question directly using this formula. You have to use ice chart before you use that, because this acid is weak. It does not form a lot of H3O+, which is required to make pH, which is required to calculate pH. So you cannot assume the concentration of H3O+ is the same as the concentration given here, 2 molar. You have to find it, which is the concentration at equilibrium. So we'll use ice chart for that matter. So how do we start? The first step is to write the chemical reaction that's taking place on here. We're gonna use equilibrium arrows again because this is an weak acid, of course, based on the Ka. It's not acetic acid, so the chemical equation should be chloroacetic acid plus water should give you chloroacetate plus H3O plus. So we need to determine the concentration of this guy using ice chart because this is a weak acid. You do that for weak acids and weak bases, and then use the concentration with this formula right here. All right. So how do we use the ice chart? How do we use the ice chart? Ice stands for initial concentration. C in the acronym ice stands for the change in concentration, and then E is the equilibrium. So this is gonna be the equilibrium concentration that we really need to find for H3O+ before we apply this formula to find pH as asked in the question. So initially, we are given 2 molar of chloroacetic acid. The initial concentration of water is negligible. Okay. And of course, if water was concentrated, we'll all be dead. The initial concentration of your product is 0 because the reaction has not started, and water does not easily ionize. In fact, the ionization constant for water is 10 to the power minus 14, which means it does not easily form H3O+. So even initially, the water itself is not going to form H3O+. So it's 0. As the reaction goes on, let's say halfway after the reaction goes on, there's going to be a change in concentration. The concentration of chloroacetic acid will reduce. That's why I'm using a negative. We reduce by an unknown amount X. Water does not easily ionize, so its change in concentration will be negligible. Okay. And then because the reacting ratio is 1 to 1 to 1 to 1, so if this is reducing by X, this will increase by X because it's a product. It should be forming with time. And this will increase by X because it's a product, again, because again, the reacting ratio is 1 to 1 to 1. To find the equilibrium concentration, we simply add this up. So if you add these two, it's going to be 2 plus minus X. That translates to 2 minus X. That's the equilibrium concentration of the acid at equilibrium. Again, water does not change in concentration. at equilibrium to be negligible, and then add this up at equilibrium. The concentration of the conjugate base, which is chloroacetate, will be X. You add this up, the concentration of H3O plus, the hydronium, will be X. Okay, in chemistry we call this hydronium. That's the hydronium ion. So we need to find this X, so we'll plug it in here before we can find the pH which is asked. To find the X at equilibrium, the concentration X at equilibrium, you will have to take advantage of the given value of Ka. You are given the ionization constant of chloroacetic acid to be 1.4 times 10 to the power minus 3. Okay, it's this value given right here. Okay, so the same K as an expression can be written as concentration of the product, can be written as the product of the concentration of the products, can be written as the product of the concentration of products divided by the product of concentration of reactants. So our product in this case will be the chloroacetate. I'm using brackets to denote concentration. And the hydronium, we divide that by the concentration of the starting material, chloroacetic acid, reacted by, multiplied by concentration of water. Now, because water is a liquid, this value right here is going to be taken to be as 1. Liquids and solid take the value of 1 in the equation of K. So Ka will be written as, you see, chloroacetate concentration is X, multiply the concentration of the hydronium, which is X, divide by concentration of acetic acid at equilibrium is 2 minus X. Okay, multiply by concentration of water. I told you it's a liquid, it's 1. So this can be written as X squared over 2 minus X. Of course, K is 1.4 times 10 to the power minus 3 is going to be equal to X squared over 2 minus X. Now, if you multiply and make a straight line expression, and make a linear expression, this will turn out to be a quadratic equation. Okay, so you know that quadratic equations are not very easily solved. So one shortcut we use, especially when you have a very weak acid like this one, is to assume that this X here has no much effect in this subtraction. Is to assume that X is 0. And there's a test to safely assume that. You want to do this ratio. If the ratio is greater than 100, then it's safe to assume that this X can be ignored. So M over acid divided by Ka must always be greater than 100 for you to safely do this assumption and ignore that X in the denominator. So to ignore the X in denominator, this ratio right here must give you an answer that's way greater than 100. So let's test and see. Our molarity of the acid, M of the acid, is 2, right? That's what the question gives us. It gives us as a 2. Divide that by the ionization constant of the acid, which is 1.4 times 10 to the power minus 3. If you divide these two, turns out the answer will be 1,429, which is way greater than 100. So it's okay to assume that this X has no effect. So that will help us to get rid of the quadratic problem. And what we're going to have here is this equation. Okay, we will know the X. So this simplifies things. Instead of solving by quadratic formula or factorization, we're simply going to use this simplified equation. Okay. to get the value of x, and do the square root of 2.8 to the power times 10 to the power minus 3, you'll find that x will be equal to 0.0529. By the way, if you decide to solve this expression right here by quadratic process, by quadratic equation process, you still get the answer to be close to this. So this is the value of x. But what does this mean? This means that the concentration of hydronium in our ice chart is 0.0529. You see, that tells you that yes, this acid right here is a weak acid because it does not give you the same 2 molar concentration while in water. If it were HCl, HCl will give you the concentration of H3O plus to be 2 molar, but this one is giving 0.0529. Okay, and that's why it's so important. It was important to use the ice chart. So now we are ready to calculate the pH. So pH will be equal to negative log concentration of H3O plus. That's always the formula. Some books will write it as this. H plus, it still implies the same thing, which is negative log of 0.0529, which is what we found in this expression right here. You do the math, you'll find that the pH of this solution when chloroacetic acid is dissolved in water will be 1.28, and that will be the final answer. So there's another way to determine that you are really right and you are okay to assume that this x has no effect. Take 2 minus x to be equal to 2 minus 0.0529 because you solved for x, right? Let's see if that changes much. Using my calculator, I see that if I do that math, 2 minus 0.0529, I'm getting 1.9471. So this proves to me that yes, it was safe to assume that the x has no effect because you see there's not much change. 1.9471 is not far from 2. So in fact, if you are to give this answer in 3 significant figures, if you are to do the quadratic formula process, the answer will still be 1.28. Okay? Or very close to that. So that's how you solve such problems when you're given a weak acid. Use the ice chart. See you soon again for more chemistry. Okay, see you again for more chemistry. Bye.